Properties of logs are important in mathematics and definitely in algebra. The problem is that as students, we haven't really seen the kind of problems that encompass logs and the algebra behind those because we haven't really worked with exponents a lot. However, we can define a few rules here to make our lives easier when we're manipulating these log functions that come from natural events that happen in our world. So if we think about two rules or two logs, a log with the same base of the product of something, we can call this the product rule. So log base A of two things multiplied together can be broken apart as log base A of the first plus log base A of the second. I want to show you where this comes from. It comes from the fact when you have a to the u times a to the v, exponential rules tell us that we can combine that with one exponent, but we add those exponents together. So remember, if you remember that log is an exponent, we can think of these products as sums. Okay, one common misconception would be that when you have log base a of u of v, that it's log base a of u times log base a of v. This just doesn't work. It seems like it might, but it doesn't. So this product rule, we're actually adding these together. The quotient rule is pretty intuitive as well. So if we have log of some base with a division, we're going to subtract those two logs. So again, this comes from the fact that when you have a to the u over a to the v, you get a to the u minus v. And again, since these logs are exponents, we can compare the division to the subtraction here, and we don't divide those logs. Finally, we have this really nice rule that will help us compute logs with powers. So if I have log base a of u to the n, what I can do is I can use this power rule to get that n out front as a multiplier. So log base a of u to the n is equal to n times log base a of u. And you can do this forward or backward. Now, you might encounter some logs that you don't know how to deal with on your calculator. So you might want some approximations because, again, logs are, for the most part, irrational numbers when we can't simplify them. So we want to find a decimal approximation for those. So if you don't have like a natural log or a common log that you can approximate with your calculator, what you can do is use this change of base formula. So the change of base formula basically says, if I have log of some base of a number, then I can change it to a different base b, and I essentially put what's inside log in the numerator and the old base in the denominator. I can do that with any base. The two that we sort of like are base 10, put what's inside in the top and what's on the base and the denominator, and log base e, so natural log. So what's inside of log goes in the numerator, and that base goes in the denominator. We use these because, of course, we can pound those out on our calculator. Let's go ahead and take a few examples here. So the first one I'm going to look at here is log base 5 of 80. I'm going to go ahead and use natural log for this first one. So I should be able to rewrite this as log of 80. So log base e of 80 over log base e of 5. So let's see what that will approximate to. Here's my natural log. So I want to use one of these so I can compute that. And it looks like this is approximately 2.723. So 2.723 is approximately log base 5 of 80. I can also use the common log. Let's write this one as log base 10 of 15 over log base 10 of 1/4. Again, I can use my calculator. So log this time of 15 divided by log of 1/4. It doesn't matter which I use as long as I use the same one. And that's going to be about negative 1.953. Let's try one more here. So log base 3 of 10, I could write this as using the common log of 10 over log of 3. So I could use a calculator there. I just want to show you something. Since I have log base 10 of 10 here, I could actually reduce this to log base 10 of 10 to the first. So this could be a 1 from the rules that we just learned over the log base 3. Still use my calculator, but I just wanted to show you that that will work for you. So 1 over log of 3, we would get approximately 2.096. And just to show you that this works with the regular log formula, we could do log of 10 divided by log of 3, and we should get the same thing. Perfect. We'll look at some examples when we come back here. The first set of examples here are just going to be breaking these logs apart. So we're going to be using those 3 log properties to break these apart. We also might use these other properties. I see I have a multiplication here, so I'm going to rewrite this as log base 3 of 3 plus log base 3 of x. I'm using that product rule of logs. You might notice that here I have log base 3 of 3 to the first. So this would be reduced to 1, basically by the inverses. And then I can't reduce this anymore. So I have 1 plus log base 3 of x. The second one, it looks like we have some division here. So I'm going to start by using that quotient rule. I'm going to rewrite this as natural log of xy squared minus natural log of z to the 4th. So I'm using this quotient rule. I have a product here, so I'm going to break those two apart using the product rule. I'll have natural log of x plus natural log of y squared minus natural log of z to the 4th, and that's by the product rule. And finally, I'm going to use that power rule to bring some of these powers down. So by the power rule, I'll have natural log of x plus 2 natural log of y minus 4 natural log of z. And this will be that nifty power rule. All right, let's look at one more here. Notice I have a 5th root here. I'm going to rewrite that as a power. We know that when we have roots, we can raise that root and make it a power. So that's going to be the 1/5 power. I'm going to start out by taking that power out in front. And the reason I would do that is so I can do these divisions and multiplications inside. So I'm going to rewrite this as 1/5 log of x y to the 4th all over 100. And that's going to be by the power rule. I'm going to break things apart here. I'm going to make this 1/5 times, I'm dividing. So log of x y to the 4th minus log of 100. And that's by the quotient rule. Now you see I do have a product here, so I can break those apart. I'll have 1/5 of log of x plus a log of y to the fourth minus a log of 100. And this was by the product rule. And you might see two things I could do here. I'm going to take this fourth power and I'm going to bring it out front. But I'm also going to notice this is log, common log is log base 10. I can write 100 as 10 squared. So notice when I have the same power, the same base on the log as my exponential, I get the power back. This is going to give me 1/5 log x plus, bring the 4 down, 4/5 log y, and then I have 1/5 times this 2, so minus 2/5. So in this last step, and that's our answer, I used the power rule here, and then this was just the inverse definition. All right, next we're going to see how to put some of these together instead of pulling them apart. We've seen how to pull some of these logs apart. Now let's put these back together. This can be something that we want to do to make things look a little tighter so we're able to know what to do with the functions. So what we're going to find out is we're going to use those steps for simplification, the power rule, the quotient rule, and the product rule, but we're going to use them sort of in reverse. Here we're going to combine two logs with the same base. We're adding together. So I can use the reverse of that product rule to put these together. I can't do it just yet because I had this 4 out in front of the log. I can only use that product rule when I have a clean slate out in front of these logs. So what I'm going to do first is put this 4 up top. So you might have noticed that usually I use the power rule sort of the last step for breaking these apart, but combining these, I'm going to use them in the first step. We'll have log base 2 of x plus log base 2 of x plus 1, all to the fourth because of that power rule. And now that gives me access that I'm adding these together. I have ones out in front. I can put these together with one log by using that product rule. So this will become log base 2 of x times x plus 1 to the fourth. I multiply these two arguments together. And this is by the product rule. And that's really as far as I can go with this one. So when we're combining, we're going to find out that we can't actually go too far because we're not really simplifying things out. We're putting them together. This next one, I noticed that I have 3 natural logs. I have a sum and a difference. But of course, what we're going to do first is use that power rule. So we'll take all those exponents and put them up into the power. So I'll have natural log of x to the 5th plus natural log of y to the 7th minus natural log of z to the 3rd, and that's all by the power rule. Next, I'm adding these two together, so I can go ahead and use the product rule to put these together into one log. I'll have natural log of x to the 5th times y to the 7th minus natural log of z cubed. And I'm using that product rule because I'm adding those and I'm putting them together in terms of one log. Finally, I'm subtracting, so I can use that quotient rule. They have to be the same logs, and they are. They're log base e, so natural log of x to the 5th, y to the 7th, all over z cubed is going to be our log simplified, and here we're using the quotient rule to combine everything into this one log portion. Okay, let's look at one more here. Notice I have this 2 out in front here, so I can actually access these product and quotient rules first. So I'm going to do that. Then at the end, I'm going to bring that 2 up by the power rule. I could do that since it's out in front, and all the numbers out in front of the natural log are 1. So I'm going to put the first 2 together by using that product rule. Next, I'm subtracting, so I can move these into 1 log by using the quotient rule. 2 times natural log of x plus 1 times x minus 1 all over x, and that's by the quotient rule. Finally, I can bring this 2 up to the exponent. That's going to equal natural log of all this squared. So everything there is squared. Now you might be saying, can I go ahead and multiply these out and make this a difference of squares, so a perfect square difference of squares? And sure, you can. So if you wanted to write it like this, good job for seeing the algebra. You don't have to, but this will work. So this would also be another good way to represent this, as long as we do legal algebra. All right, we're going to wrap this up by looking at some applications. There are a lot of applications of logarithmic functions. Remember that these are the inverses of exponentials. So when anything sort of grows or decays quickly, when we're trying to solve that or relate two things together, we can use logarithms. The first thing we're going to look at here is, if you're taking chemistry or have an interest in that, is the pH of a solution. So the pH of a solution is defined to be negative log base 10 of this hydronium ion, H30 plus, H3O plus, where H3O plus is the concentration of the hydronium ions in moles per liter. We can actually use our calculator to go ahead and compute that. And you can compute that solutions with pH less than 7 are said to be acidic, while those greater pH than 7 are basic. So when you're thinking about making solutions, making your garden be a little more or less acidic, thinking about things that you're eating, you can think about the pH, and we can solve that by using logs. Another sort of applicable application here is called the Richter scale. Now, I know in the Midwest we don't have too many earthquakes, but we can measure that earthquake intensity by the Richter scale. So the Richter scale basically provides a number, usually between 0 and 10, that will give us the intensity of that earthquake. The largest intensity I've ever heard of, I think, was a 9.8 or so, or 9.2, and that was in Alaska. It wiped out a whole town. The earthquakes that we have in the Midwest are more like on the order of 3 to 4 on the Richter scale, and usually these days they come from fracking. On the West Coast, every once in a while, you'll get a 6 or a 7 magnitude earthquake, and that will do a lot of damage. So when you're looking at the intensity, we're using this log. So the intensity is going to be in powers of 10 greater than the number on the Richter scale. So I sub 0, I naught, is the intensity of a just discernible earthquake. I is the intensity of an earthquake being analyzed, and R is its marking on the Richter scale. So R is equal to the log of that earthquake intensity over the intensity of a just discernible earthquake. We can think of this in terms of sound too. And the decibel formula follows a very similar formula. So the I naught, which is the intensity of a just discernible sound, um, I is the intensity of the sound being analyzed, and D is the decibel level. It's given by D is equal to 10 log of I over I naught. So we can go ahead and analyze these things in terms of decibels. And I have an example for you to consider. So the Kansas City Chiefs boast the record for the loudest decibel record ever recorded at a sporting event. The record was recorded on September 29th, 2014 at a decibel level of a staggering 142.2. So if you're driving around the Kansas City area, you might see some 142.2 stickers on the car in red and gold, and that is in memory of this event. If we're given I naught is equal to 10 to the negative 12. So 10 to the negative 12, that's scientific notation. Basically, we move the decimal back 12 places. So we have 0.10 zeros, 1 0, watts per meter squared, very small, just discernible sound. What is the intensity I of this sound? So we think about this in terms of powers of 10. We can use our formula. D is equal to log 10 log of I over I naught. That's right here. And we can plug in. So the decibel level recorded was 142.2, 10 log of I, which we're trying to find, over I naught, which is 10 to the negative 12. If I'm trying to solve this for I, the first thing I need to do is get log by itself. I could put this 10 up top, but if I want to get rid of it and get it over here, isolating I, I'm going to actually divide by it. When I divide by 10, it moves my decimal back one place. So I have 14.22 is equal to log of I over 10 to the negative 12. I can now use my quotient rule to sort of break this up. Again, I want to solve for I. So the better I can get this separated, the better I'm going to work out with the calculations. I'm going to use the quotient rule to write this as log of I minus log of 10 to the negative 12. Now, we're almost getting this I isolated. Remember that log is log base 10. This is log base 10 of 10 to the minus 12. So this whole term becomes the exponent as minus 12. We get 14.22 is equal to log of I minus a minus 12. We know that this is plus 12. And again, in the spirit of solving for I will go ahead and move the 12 over to the left-hand side. So if I subtract 12 from both sides, I have 2.22 is equal to log of I. Almost there. I noticed that I want to solve for I, but it's inside a log. So we know that we commonly are going to go ahead and rewrite this as an exponential. So I'm going to go log to exponential. Remember that log, whatever that log equals, 2.22 is the exponent. We must raise the base 10 to in order to receive what's inside the log. So now I just need to compute 10 raised to the 2.22, and I get a staggering 165.959, and that's going to be in watts per meter squared. Just for point of reference, this intensity of sound is louder than a jet engine. So they were really coming that day for that record. All right, well, I hope that this has helped you with some of the properties of logs. They're really important, but once you get these rules down and some practice, you should be just fine.